So here's your summary about scientific notation, and this is how interpreted. Just remember that this is always some sort of power of 10. So you know, if you take 10 raised to the first power, it's just 10. And of course, any number raised to the 0th power is 1. So you have an exact 1 if you write it down like this. Also notice that when I write it in my own examples, you don't have to use the plus. Plus is optional. So if you need to specify the negative power, then you use minus, but it's a matter of style. You can write it with the plus, or here I just show it to make sure that we have the difference between the negative powers and positive powers. Okay, so also just something else is a normalized scientific notation. So typically, because of such a flexibility that you can express fractional numbers multiplied by this 10 raised to a certain power, it's possible to keep the absolute part, which is the number that comes before exponent part, just possible to keep it in range from 1 to 10. And if that's the case, such scientific notation is recognized as a normalized scientific notation. But this is just a technicality. Really, this exponent would work with any others. And of course, this is for fractional numbers. You don't use this with integers or any other integral data types, this e suffix, because this is only for fractional numbers which are stored to a certain precision. In our example here, I already introduced this final keyword, and this is how you declare constants. So constants are very good thing. They improve performance. They are very safe because the only action that takes place, like my epsilon assignment was, or initialization, was taking place only once, and this is all we need to do here to create it. And then, you know, arguably, if I just written something like that, that would do the same thing. However, you should probably recognize that this gives much more meaning to the entire statement here, because we're checking the difference, which should always be positive, and making sure that it does not go above certain ceiling, and normally it's called an epsilon. Okay, so these are more examples for you. Also, it is a common practice in Java to name constants with an uppercase notation and use underscores between the words. Just a note. So here I could use like an uppercase name for this, but I'll just leave it like this. Right, so this is a capitalization of the names of constants. Arithmetic operators, just very briefly, you know about addition, subtraction, and multiplication. With division, things slightly differ. We have two types of division, which is specific to dividing real numbers or fractional numbers versus division of integral values in integral data types. And with both, you can use the modulus operator, which will return the remainder of the division. All right, so this is just something special about division. And so let's try something like, let's try to add another example. I'll move this out of the way one more time. Okay, like that. And just to show you that in Java, if we attempt to divide by 0, for instance, if I have a scanner sc equals new scanner system dot in standard input, and if I do this, I need to import the scanner, which I typically right click and say fix imports inside NetBeans. So it just tells me that okay, there is one scanner found in Java library in the utilities package, which is fine. And now I can say that double, let's start with the double divider equals, or divisor, let's call it divisor, equals scanner dot get, actually not get, next double right here, next double. So that should give us the double from the keyboard when we run this program. And I will try to system dot out dot print, just print the number, print line, print the number. We'll just say like 1 divided by this divisor. Okay, so something as simple as this. And for clarity, let's just use a literal for the floating point right here. So just pretty simple idea, just very quick check, run it. I don't even have any prompts, it just waits for my input, and I will just enter 0, and let's see how this behaves. You see that this prints an infinity. So print line, when we give print line an infinity value, it prints it as infinity. So let's just do it this way: double result equals something like that. And you see, as I am trying these little tiny versions of what we're discussing here in this presentation, you see it already is taking some experimentation. And this is what I would encourage you to do all the time. Don't take anything for granted. You need to test as much as possible, and you really need to be practicing those tiny examples with just few lines of code and see how everything works. And this is part of your reading assignment. Not just read, but take every coding example that you see as a challenge, as an opportunity to experience it. And how else can you experience it? You just need to open the coding window like I do here and try it, right? So that's the way it goes. So I just took it out like this, and you see that it becomes an infinity, which is, by the way, a special encoding of double. But now I will try something else, right? What if I try to print 2 multiplied by this infinity? That's the reason why I created this variable, because I would like to repeat it the second time. Okay, and so it waits for my input. I run it. Yeah, so once stuck with infinity, it remains the infinity, as you can see. So this you know, infinity multiplied by something else and so forth is just doesn't work like this. We can even try to divide it again by this divisor, which I intentionally set as 0. Okay, and run it. So 0 again, and yeah, so it just stays an infinity like this. So just for your information, this is how it behaves with fractional numbers, which is the type of double. If I change this, so I just copy and paste this down here to preserve it, and change it to an int. And if I make this int next integer, right, integer like that, and of course the result also will be integer. I'm switching to an integer. So here we need to update this to be just just a integral literal constant right here, and we'll just try exactly the same thing here. Get next int, is it an int? Next int, yeah, it's next int. Okay, so save this, run 0, and look, now the behavior of this program is totally different. It throws an exception, which is an equivalent of a runtime error. There's a special handling in Java Virtual Machine when you attempt something completely illegal. It identifies the situation as arithmetic expression, division by 0. So of course, when something like this happens and you have your project open, once again, remember, you can always click on, like you locate the very first error message like this or exception message like this. You click on it and it tells you, look, this is happening very likely right here. So it just knows the number where things may be happening. The only way around it is, there are actually some ways around it, but what you could do is just compare divisor with 0 and avoid an exception by doing this. But we also can catch this exception, and this will be discussion of future topics when we talk about exceptions. One more thing to wrap this up very quickly. Let's just change this to something like 11 divided by the divisor. So I'll just change that to something else, and now, you know, run it again. And this time, instead of 0, I will enter something like 7. Okay, 11 divided by 7. Of course, the result is 0 this time, because what happened was that now it's integer division, and integer division giving us the result of the division without the remainder. So that's what's happening. If I change this to modulus operator, also informally known as remainder operator, like this, and just to show what the remainder is, and try the same input, my divisor is 7, so we are dividing 11 by 7. Okay, so we get essentially 1, and the remainder is 4, right? So that 7 fits inside 11 only once, and the remainder is 4. So now it's printing this remainder, and that line really just is not necessary right here. You can get rid of it. Just wanted to show you the use of the remainder. Now, the remainder operator can be very, very, very useful. The most obvious, for instance, use of it could be to determine whether the number is odd or even. So let me change this program. Instead of using this as a divisor to get the input, I will get the value. Okay, I will get this value, and I will say, how about result equals value divided by 2. Okay, and so now what I can do is if result does not equal 0, right here, this would mean that the number is even. So I'll just move this statement. Just print this is an even number. How about I use the value and concatenate it here and say value plus even. So this will print even. Otherwise, I'm sorry, if it does not equal, so if it equals 0, that will be an even case. Okay, so here we just print odd, and we could, of course, run this inside a loop. Where should we use this loop? I think, before we get the next integer. So we initialize the scanner, and then we can have this endless loop, true, while true, something like this, endless loop, just so that we can test our stuff. I move all of this inside, and I highlight all these lines and press tab to keep the spacing correctly. Okay, so this is the closing brace of the while statement, and this will be just, this will keep it looping and looping and looping. So let's run this code. So again, it's just waits for an input. I should probably print some kind of prompt, but let's try some numbers. So number 1, for instance, is odd, right? And number 2 is even, so it prints even. Minus 100 is even, and -7 is odd. So you get the idea, because this is the remainder, and of course if you take an odd number and divide it by 2, then you in the odd number situation, you always get the remainder 1. And that's just a standard practice to detect whether the values are odd or even. By the way, 0 would also fall into this category if we try it like this. Okay, so these are examples of some of these operators for you. And we also need to discuss increment, decrement, just very briefly at this point.